Next up, we have Alexander Turner from Harvard University. His field of study is atmospheric science. Advisor is Daniel Jacob, and he did his practicum at Lawrence Berkeley National Laboratory.
Thanks for the introduction. So I'm actually now starting a postdoc at Berkeley, and broadly, I focus on the carbon cycle. The molecules that I focus on are methane and CO2, and these two molecules are important because together they're the two strongest greenhouse gas forcers, and together they account for more than 85% of the atmosphere, of the forcing. So what that means is that changes in the atmospheric abundance of these two molecules will have a profound impact on the state of our climate. And understanding the processes that govern their atmospheric abundances is critically important if we want to understand how our climate might change going forward. So what I'm showing here is the atmospheric concentrations of these two molecules over the past few decades. And we can see that CO2 has been increasing pretty rapidly over the past few decades with a strong seasonal cycle. Whereas methane, on the other hand, was increasing pretty rapidly in the 80s. Then right around 2000, it stopped increasing until 2007 when it started increasing. And we really don't understand the processes that are responsible for these trends we're seeing in atmospheric methane. And so this is something I spent the bulk of my PhD focusing on. But today I'm actually going to talk about some of my CO2 work. And this CO2 work was actually my CSGF practicum, and I thought I was going to be unique talking about my practicum, but apparently David did as well. So today I'm going to talk about network design for quantifying urban CO2 emissions. This was published in 2016. So what I'm interested in is understanding the fluxes of CO2, and there's a couple ways we can do that. On the left, I'm showing a little cartoony example of how we might do that with a bottom-up approach. In this case, you take some activity data like the traffic density and emission factor like the CO2 per car, and the product of those two gives you a map of CO2 emissions. And this is great because then you are relating the CO2 emissions to their underlying physical processes. But they're subject to pretty large uncertainties. How well do we know the traffic density? Is our emission factors actually representative of all cars? The other approach is to use atmospheric observations and try and back out what those fluxes should be or improve upon our prior knowledge of those bottom-up inventories. And this is what I spent the bulk of my PhD working on. So before I get into that So for the actual practicum, what I did was go and work with a group that primarily makes atmospheric measurements and doesn't actually do that much computing. But there was a lot of low-hanging fruit that we could use, that I could focus on to try and help them improve their observations. So really what I was focused on doing is understanding what's the best way to observe CO2 in an urban area and improve our estimates of those emissions. So what I'm showing here is a cartoony example of the number of observations on the x-axis and the noise in those observations on the y. And we might have some current observing system here, and the most error reduction would occur when you have a lot of observations with little noise. So you want to get down here, but in some cases you might be limited by the noise in your system or the number of sites, and understanding what's the most cost-effective way to reduce the error in our estimates is the project that I was working on. And for this project, I was building on the work from an existing network they put together called the BEACO₂N network, the Berkeley Atmospheric CO2 Observation Network. And the idea that this group at Berkeley had was they wanted to have a network of cheap sensors in the Bay Area and sort of blanket the whole domain and see if that's a better way of estimating urban emissions. And so I was coming in to do some modeling for that work. So before starting, I wanted to build a bottom-up inventory to have a good prior model for our CO2 emissions. So the Bay Area Air Quality Management District provides county totals for CO2 emissions, with most coming from transportation and industrial commercial, and some from electricity cogeneration and residential fuel. But what they also provide is this table of sources. And in the Bay Area, the biggest sources tend to be places like Shell, Chevron, Tesoro, ConocoPhillips. And they also have some more exotic sources, like the Jelly Belly Candy Company at 1 Jelly Belly Lane, emitting about 5,000 metric tons of CO2 per year. So this table covers most of the industrial, commercial, and electricity cogeneration sources. We can then map the residential fuel usage to population and scale it with temperature. And for this work, I was neglecting these two small sources. And that just leaves transportation. And so for transportation, we then use this traffic inventory called 5, and we use natural fluxes from Carbon Tracker. And so putting these all together, we get this regional inventory here on the left at 1 kilometer resolution for the Bay Area. And for reference, on the right, what I'm showing is a global inventory of CO2 provided by Edgar. And this was actually sort of state of the science for what we had for gridded inventories of CO2, with this box being San Francisco. So what we put together already has quite a bit more detailed information. So then moving on to the top-down methods, the way that we actually use these atmospheric observations to improve our inventories, pretend we have a site here in the Bay, and we make measurements for a week that come, say, through the Golden Gate Bridge here, and we measure CO2 concentrations that are generally low with some variability. Then during the second week, we have air masses that take this different trajectory, sort of following instead the highways. And during the second week, we measure, again, somewhat noisy, but much higher concentrations. This would imply that somewhere along this path, there was an urban source. We can state this a little bit more formally by saying we have a vector y of measured concentrations, x is the fluxes that we're interested in, and h is a matrix that maps between those fluxes and the observed concentrations. So solving for y is known as forward problem. You measure the fluxes, map those through your footprints, and you get some observations. This is a well-posed problem with a unique solution, whereas the converse is an inverse problem and may not have a unique solution. However, if you make some simplifying assumptions, like in our case the problem is linear, if you make the assumption of Gaussian errors and formulate it as a Bayesian inference problem, you get this solution. So XA is, in this case, the prior, or that bottom-up inventory. And so you can see that everything is building upon that prior. So this is your starting point, and you have deviations from that. So in my case, what I'm doing is I'm using Edgar as the prior here, because this is an inventory that's available anywhere in the world. If I wanted to set up some observing system, I could use this as my prior. This H matrix is the matrix of footprints that maps between those fluxes and the observations. And we construct this using a combination of the weather research and forecasting model, which is a numerical weather prediction model, and the stochastic time-inverted Lagrangian transport model, which is a particle dispersion model. And what these do is they allow us to compute the footprint. So what we do is we specify a set of receptor locations, which are spatial temporal locations where we make a measurement. And we advect particles backwards in time from those locations to see where they might have come from. And in cases where those particles are near the surface, we assume that they might have been sensitive to emissions that would have occurred there. And so we can take these trajectories, and turn them into footprints. And so what I'm showing here on the right is the average footprint for the whole network, shown here on the left. And so these are all the potential sites in the Bay Area that we have. So that's how we construct that H matrix. The Y matrix the Y vector, is the vector of observations. And in this case, we're using synthetic observations that we generate from this high-resolution inventory. So what we can do is we can take this inventory that's much finer in both spatial and temporal detail, multiply it by this footprint matrix, and add noise that's representative of different types of observing systems. So for example, if you have noisier observations, you can add more noise to it, you can add biases, etc. And then it also allows us to get rigorous error estimates. This R matrix characterizes the error in the observation system. And then this B matrix is a pretty interesting one. So in my case, what I'm interested in looking at is fluxes at 1 kilometer resolution at hourly temporal resolution. And so it ends up becoming reasonably high resolution with about 2.1 million state vector elements. So this B matrix would then be 2.1 million by 2.1 million. But there's a lot of information we know about it. So we can actually break it up into a temporal component, which here we're calling D, and a spatial component E, using a Kronecker product, which is basically like an outer product but extended to matrices. So this temporal component, we just give it a 3-hour temporal length scale, so that's saying there's some lag in the system. So fluxes at 1 hour are related to fluxes at another hour with an exponential decay. But the spatial component is really interesting, because there's a lot of things we know about how fluxes might covary in an urban domain. So for example, if we were to measure some fluxes coming from the Bay Bridge, and we say they're underestimated at one point on the bridge, presumably other parts of that bridge are also underestimated because a car probably drives the whole length of the bridge instead of, say, going off into the water. Conversely, the ocean pixels probably respond similarly. If one ocean cell is underestimated, other parts are probably underestimated because they're coming from the same ocean model. So what this gives us is 8,000 little Gaussian blobs for each one of the pixels in our spatial domain. And this is a little animation showing some of those little blobs. So we then reshape these into vectors and put them into the E matrix, which gives us this nice diagonal structure, or banded structure. And so this is how we construct that B matrix. So we can then put this all together, and what I'm showing here is some example output. So on the left, I'm showing those prior fluxes. In the middle is the posterior. And so you'll notice that the biggest changes are occurring here in the East Bay, which is where we have most of our observations. Far from our observing system, we have little to no changes because we have no sensitivity there. And on the right, I'm showing the truth. So what we can also do is look at integrated areas. So if we look at this urban domain here and integrate the fluxes over this area, that's what I'm showing in this bottom left panel. So the green line is the prior fluxes, the black line is the truth, and the pink is the posterior here. So when we integrate over this larger domain, we do quite well. And then finally, what I'm showing here is the deviations from that prior, so the posterior minus the truth, and this is the posterior minus the truth, sorry. So what I was interested in looking at is how well we can resolve different types of sources in the Bay Area. So how well can we resolve, say, an area source, or a line source, or different point sources? And so now what I'm showing on the left is really the quantitative version of that cartoony plot that I showed at the beginning. So on the X, I'm showing the number of sites in our observing system, and the Y is showing the mismatch error in this observing system. And so again, our best estimates are coming when we have a lot of sites with little noise. But what we're sort of also noticing is there are these regions that seem to develop. So above this red line is sort of a noise-limited regime, where if you were, say, sitting at 5 ppm error with, say, 20 sites, increasing the number of sites in your observing system won't really improve your estimate of CO2. You really need more precision. Conversely, if you're down here with, say, 2 or 3 sites that are all pretty precise, you really just need more coverage. You're not going to get a better estimate by improving your noise. And then we also looked at this for the different types of sources, so the line source and the point source. And what we find is that for things like a point source, this red line shifts up. And that's not entirely surprising, because if you have an enhancement coming from a point source, that enhancement is going to be quite large at your observation site. Whereas if you're trying to quantify the entire urban domain, you need to be able to resolve some of those smaller fluxes with more accuracy. So a lot of this is fairly intuitive, but it's nice to have sort of a quantitative map showing, helping to guide future observing systems. And so that was really the goal of this practicum project that I worked on, was to help guide the future development of this observing system in the Bay Area. And then, so more broadly, the main objective of my PhD was trying to understand the carbon cycle, and this was one project contributing to the CO2 piece. And it really wouldn't have been possible without the CSGF, because this was a practicum project, and I really appreciated the freedom that I got from the CSGF. So with that, I'll take any questions you might have. Thanks.